Okay, so now I'm going to be explaining some of the important questions that can be asked in your exams. So firstly, we've been given an encoding function e, which is from b squared to b5, and these are the code words that we have to prove are a group code. So firstly, we make a composition table in which we perform the binary addition of each of the elements with each other, and these are the final values after the binary addition. So for closure property, we can see that all the final answers are the same as the inputted values. So supposedly if we take this as A and this as B, then this is our answer. So this already does belong to B raised by 5. So for all A comma B belonging to B raised by 5, A star B also belongs to B raised by 5. Therefore, this property has been proved. Now for associativity, we have to take any three values such that a plus b whole plus c is equal to a plus whole of b plus c. If we take these three values, then first performing the LHS side, we perform the addition of these two values first. So we get this plus this, which gives us this. So we replace that value over here and then we do the addition with this. Now, so this is our first value and then we perform the addition with this value. So we get the answer as this and we write that down as our LHS answer. Now, if we perform the addition of this and this first, so we get this and this. Yeah, so this is what we get first. So we replace that value over here and now we perform the addition of this with this. So we get the final answer as this, which is the same as RHS. And if you take any other combination of three elements, you will see that it's true for all possible combinations. Therefore, associativity has also been proved. Now, the identity element is this because we can see that this under binary addition with any other element gives us the element itself. Therefore, that is the identity element. Now, if you pay attention, the binary addition of any number with itself gives us the identity element, which is 5 zeros. Therefore, the inverse element is each element is its own inverse. Now for commutativity, we can clearly see that addition of this and this gives us this value. But if we reverse them and we do the addition of this plus this, that also gives us the same value. Therefore, the commutativity property has also been proved. Now, Hamming distance is very important because it helps us to find out how many errors we can detect and how many errors we can correct. Now, Hamming distance is found by the binary addition of two numbers. So, as we can see, the binary addition of this plus this gives us 1 0 1 0 1. Now the mod of this value is equals to 3. Therefore, that is the Hamming distance. And as you can see that there is no other value less than 3. So this is the minimum distance um, out of all the possible combinations that we can imagine from the group. So as per the theorem, if the minimum distance is equals to k plus 1, then k is equals to the number of error detected. Therefore, the number of errors detected is 2. By the second theorem for correcting errors, the minimum distance has to be equal to 2k plus 1. Then k is the number of errors corrected. Therefore, 1 error is corrected. Moving on, we have another question in which we have an encoding function e, and we have been given a generator matrix. So the generator matrix is very important because with the use of the generator matrix, we can make the code words that are very important for coding theory. So the generator matrix is given as a combination of an identity matrix of size m, and m is this size and this is n size. So G is equals to IM dash A. This means that this is the identity matrix and this is the matrix A. So in order to get a parity check matrix, which is denoted by H, we take the transpose of A and the identity matrix of size n minus m, which in this case would be 3. So this would be our parity check matrix. But I will explain that in the next question. In this question, I want to focus on generating the code words. So the elements belonging to B square are 0, 0, 0, 1, 1, 0, and 1, 1. So in order to find the code words of this, what we do is we take the word, the original message, like 0, 0, and we multiply that with the generator matrix. So when we multiply 0, 0 with the generator matrix, all these elements will be 0 because 0 multiplied and added with anything is 0. So we move on to E of 0, 0, 1. Now when we multiply 0, 1 with this matrix, so in this first case 0 into 1 plus 1 into 0. So this will be 0, 0 into 0 plus 1 into 1. So that'll be 1. Now this is 0, 0, so again 0. Now this is 1, 1. So 0 into 1 is 0, 1 into 1 is 1, and same for here. So this will be the code word generated for this original message 0, 1. Now for 1, 0, similarly, there's only difference in these two spaces. So over here it becomes a 1 instead, only these two are interchanged. So this will be the code word generated for 1, 0. Now for 1, 1, for this it'll be 1 and this it'll be a 1 and this will be a 0. Now if you multiply 1 into 1, then we add 1 into 1. So as we recalled earlier, 1 plus 1 gives us 0. Therefore these two spaces over here will also be 0. So this will be the code word generated for 1, 1, and these are the eventual code words, sorry. So our last question is based on the parity check matrix, and in this we've been given an encoding function E from B3 to B6 and a generator matrix G. This is the given value. So how to find out the matrix H? We've seen that the given matrix G has a matrix inside it which we denote as A. So we have to write the transpose of A in H. So as you can see that this is the transpose of this part, and this is the identity matrix of size 6 minus 3, which is 3. So this is our final parity check matrix. Now these are the given encoded words, and we have to find out if these are valid or not. So the process is very simple. We have to multiply, so R refers to these encoded words, and so we have to multiply the parity check matrix with the transpose of these encoded words. So in the first case, we're multiplying the parity check matrix H with the transpose of this. So after we perform the multiplication, we get the answer to be 0, 1, 1. Now what we have to do is we have to look for this value inside this. So as you can see, it comes in the second column. So the second column, this signifies that the bit in the second column of the encoded word is not right. We have to change that. So after we change whatever this value is, if this was a 0, then we would have to change it to a 1, but it's a 1, so we change it to the 0. Now the first 3 digits of the encoded word denote the original message. So after changing, the original word becomes 100, and after changing, the encoded word becomes 100, 110, which would have been right in the first place, as this is not right. 110, 110 is not right. The correct answer would be 100, 110. Similarly, we take the second example, which is 111101. Now after performing the multiplication, we get 101. Now that corresponds to this column. So therefore we change this value from a 1 to a 0. Therefore there's a change in the first 3 values, so the original word will also change. Therefore the original word becomes 110, and the encoded word becomes 110101. That's pretty straightforward. Now, if we have a case in which none, like this value does not correspond to any of these values, And since there's 6 values already here out of a possible 8, the other two values that are missing are 000 and 111. Now we'll see the case for that. Now, if we take the third case in which the encoded word is 6 zeros, and after multiplying, obviously the row will be, the answer will be 3 zeros. Now, what we get is, if the answer is 3 zeros, that means the original message is 3 zeros, and the encoded word is also 6 zeros. That means the encoded word is correct, but the original message is 3 zeros. Okay, so we have a case in which we have all ones, and the answer in this case will come out to be 111, because there are three ones, and after multiplying three ones and adding them, we get a 1. So, when the answer is 111, it is not corresponding to any of these values. Therefore, we cannot decode the given R value, which is 6 ones. Therefore, there is no original message, as we cannot decode this value. Now, we get a value which is 110111. Now, after multiplying, we get 010. Now, this is not in the first three values. So, irrespective of that, it's corresponding to the fifth column. So, we change the fifth bit, which is 1. So, therefore, the R value changes, but the original message does not change. This means that the given value, R value is wrong, but if we change one bit, which is the fifth bit, we get the original message, which is already there in the value R. So it does not matter if the value that we receive on the answer side is in the first three values or not. We just have to change that bit. And if it does not change in the first three values, then the original message does not change. It stays the same, but the R value changes. So that's it. Thank you guys for watching.